Hi guys, Kenna here. Today we're going to be looking at kinematics. Now, this is probably one of the more difficult areas in term one when we go ahead and start looking at mechanics. The only other one that's kind of in the same ballpark is maybe collisions. We'll see where that falls if we get to it this term or next term. But kinematics is really about paying attention to details, making sure that you identify the variables that you know and identifying the variables that you don't know and being able to use that information to go ahead and solve for what you're looking for. Okay, so let's go ahead and take a look at our essential questions for today. All right. Number one, how are horizontal and vertical motion related in terms of a projectile? Now, we'll talk more about this next week when we're actually doing projectiles, but I think it's valuable for us to start kind of pre-teaching it now and realize the value of this kind of independence of motion in two different planes. Okay, so we'll come back to this again. This is not the only time you'll see this portion of it. Number two, what is the center of mass versus the center of gravity, and how are they related to each other? We'll talk a little bit about these two terms. They're probably new to you in terms of their vocabulary, but not necessarily new to you in terms of the way your brain thinks about the interactions with the environment around you. And number three, how do you select the appropriate kinematic equation to solve for your needed variable? And this is probably the most important one and the focus of what I really want you to get out of today's lesson. Okay, not just the notes here, but also the practice problems that we'll go ahead and do. Before we go ahead and get started, I want to go ahead and review vectors a little bit. Now remember, we have vectors versus scalars. A scalar measurement has a magnitude but does not have a direction, whereas a vector quantity represents both a magnitude and a direction. And we've gone over several different examples of this thus far. These vectors can represent a force or what we've already covered, velocity or acceleration. So remember, velocity and acceleration are both vectors because they have a magnitude and a direction. Okay, so let's consider velocity for a second since that's the one we've spent the most time with. A velocity of, say, 5 meters per second that is applied in a particular direction can be applied at any particular point in space. In other words, that point from where the velocity starts does not change the actual velocity itself. You can move it. This is where that frame of reference that we talked about before becomes so important. Velocities are independent of their particular point of origin. To define a velocity, all we need to know is the speed of the object and the direction in which it's headed. This is going to be valuable in terms of the vector voyage that we did before on Wednesday, because that allows us to go ahead and think in terms of adding up these vectors to go again get a resultant force or a resultant velocity or a resultant acceleration. Now, this same idea holds more generally with vectors in general. Okay? Vectors only impart magnitude and direction, and therefore don't impart any information about where that quantity is applied. And this is an important idea to remember when we study vectors. Because of this, we can actually go ahead and create, you can call it vector addition or vector subtraction, but it's really both kind of the same thing. But you essentially can take two components to make any resultant vector. And this is true for no matter what direction that particular vector seems to be pointing. A force vector that is directed upward and to the right has two parts, the upward portion and the rightward portion. That is to say that if you pull on an object in an upward and a rightward direction, you are exerting an influence upon the object in two separate directions, an upward direction and a rightward direction. And these two parts of the two-dimensional vector are referred to as component vectors. Okay, so this idea of component vectors is important, that I can take any vector and I can break it down into components. Now, we do this a lot, and if you do this kind of addition in your math classes, it should look somewhat familiar. So you have essentially what we would call the x component or the horizontal component and the y component or the vertical component. And you can do this with any vector. The sum vector, or what we would call the resultant vector, is the combination of the two component vectors. So you can take component vectors and create the resultant, or you can break the resultant down into the two component vectors, as you can see below in the diagram. So that's an important thing when we start looking at motions in different directions in terms of space. We also want to go ahead and think about, well, where does this motion act upon? And one of the terms that we kind of use in physics is what we call the center of mass versus the center of gravity. Now, gravity occurs from the center of whatever the object is. That does not necessarily mean that that is the center of mass, because we can look at systems. And this becomes really important when we start thinking about why things like Pluto get demoted. Okay? Pluto, I know you may think it still should be a planet. It was for a long time, but its characteristics are more indicative of what we would see in a dwarf planet, and that is why it was demoted. And one of the biggest reasons we look at is that the center of revolution, okay, in terms of it with its larger moon Charon, is not inside Pluto, but external to Pluto. So Charon doesn't orbit Pluto, they both orbit each other. And this is because of where the center of mass is for the particular system. So the center of mass of an object is the point at which the entire mass may be considered to be concentrated. When we draw free body diagrams, which we'll do a lot more next term, not next term, but next unit, is based is the point at which the object is considered its kind of center where all the different forces act upon. Okay, this is true also for any motions. If you have motions going in multiple directions simultaneously, where do they act upon? And this is not perfectly true. You can think about a football player running down the field. Somebody hits them at the top half and the bottom half. Their body can go two different directions, send them in a spiral, these types of things. And so the idea of a center of mass is the point that represents the bulk of where that object is going to move from. So it's a fixed point relative to that object, but it does not necessarily lie inside the material of the object itself. If we think about like a hula hoop, for example, a hula hoop has all its mass in the outside part of the ring, but the center of that mass is actually going to be in the very center of that ring. There's no actual material there, but that's the center of the mass from which all of the movement of that object is going to be regulated. So if the object is located in the gravitational field created by, say, a star or a planet or anything like that, it also has a center of gravity at which the entire weight of the body may be considered as concentrated. Now, the center of mass and the center of gravity are often the same point, but they don't have to be. Okay. And so we got to kind of keep that in mind as we go ahead and move forward. Okay, there's your center of mass in the middle from where all the vectors are leaving. It's important to understand these concepts because these actually impact what we would call stability. The center of mass helps us to understand when objects are going to be stable or unstable. If their center of mass is in a position where it is unlikely to be shifted heavily in one way or another, it is stable. Okay, so this is where the idea of a lower center of mass is important. And if any of you do electrothon, okay, the electrothon cars, this is an important thing. When you start going around a turn, you want a low center of mass so that when you go around that turn, if you get too high and you turn the car, you don't end up rolling it. Okay, so this is kind of what we want you to think about. You can think about playing the game Jenga, right? If your center of mass gets too far off that center line, as you start adding more pieces up on top, the tower is going to fall over. Okay, so if you have Jenga, I would encourage you to try playing a game with your family and think about this in terms of the center of mass and what that does to the stability of the tower that you're working with. Homes, they have to keep this in mind in terms of houses so that if there is a landslide or anything like this, the house doesn't just slide off the cliff. Now, this gets difficult a little bit when we think about unusually shaped objects. If you think about the gymnast here on the left, she's able to stay balanced here because of where the center of mass is. The center of mass line is still down the center, even though her legs are hanging off the side. If you take a look at a hammer that's thrown and spiraling, this is true for if you do like axe throwing or something like that, you can see that the center of mass stays pretty much in the parabolic arc, even though the handle swings up and down and makes the trajectory look much less fluid. Okay, but if you were to take a hammer, go ahead and paint a nice little yellow dot on it, and then go ahead and toss it, you would see that it simply goes up and down just like a ball would or any other object. So let's take a look at a couple of examples. A bicycle, smaller wheels such as those found on dirt bikes, are more maneuverable and lower the bicycle's center of mass. This makes it easier to stay upright and perform tricks even on uneven terrain. And so this is why when you see all the BMX guys, they don't have these giant tires that we would typically see in like a racing bike, okay, where the surface is smooth. For the uneven terrain, it's nicer to have a little bit smaller wheels, makes you more maneuverable. When we start looking at something like a javelin throw, I know lots of track analogies, but track's a thing for me, so that's what helped me understand it. The javelin is a shaft of wood or metal shaped like a spear, and it's got a big metal tip at one end and a grip bound around the shaft at the center of mass. The javelin must be held by the center of mass when thrown, otherwise, it's just going to kind of be a wounded duck. It's going to flip over the top of itself. And so, if you ever watch people throw the javelin, especially really good javelin throwers, the motion stays consistently smooth as they pull their arm up over the top so that when they get that release, they're releasing with the hand right there where the center of mass pretty much is. That keeps it from doing much wobbling, keeps it much more balanced. And then if they can get a nice little flick as they go out, it gets a nice little spiral. You can get some really good distance. And hopefully the point goes into the ground so that you can measure from the point rather than from where the tail hits. And then lastly here, rotation of the Earth and Moon. You've been told that the moon revolves around the Earth, and this is mostly correct, but not entirely correct, because the Earth also revolves around the moon. The reason the Earth is still considered a planet, unlike Pluto, is that the center of mass for the system, for the Earth Moon system combined, is inside the Earth. So, this is what we would call the Earth dominates its own orbit. And this is why things like Pluto are no longer considered planets, because that point of the center of mass for the system is external to Pluto so that it does not dominate its own orbit. Okay? So the composite body has a center of mass, and where that center of mass is located determines whether or not it is a planet or a dwarf planet. That's one of the key criteria that we start looking at. Okay? All right. Now, when we do drawings, I've asked you to go ahead and do diagrams or drawings when you do these word problems because it really helps you to visualize what's happening. And if we're going to do a frame of reference that requires a positive or a negative, we need to be able to know which direction we labeled or identified as the positive direction. Okay. As we get into kinematics today, this becomes even more important. Okay, because we may start looking at things that are accelerating or decelerating, and we're looking for distance instead of speed as we're doing our calculations. Okay, essentially, these are vector diagrams. We're going to look at velocity, acceleration. What direction is the velocity acting in? What direction is the acceleration acting in? How is the car moving when that begins to occur? This helps us to establish our frame of reference so that when we make the calculations, we can make them simpler and provide accurate representations for the events occurring, whether that's by making sure we understand direction or whether it's by breaking out a vector into its component vectors. And this is going to require us to do a little bit of our geometry, okay, Pythagorean theorem, that sort of stuff, so that we can identify the resultant vectors at the end of our calculations. Now, there are four major kinematic equations, and I've included them here. They can be utilized to predict unknown information about an object's motion if the other information is known. And they've been well tested, and so they're very valuable. But you can see that we're going to definitely have to do some algebraic manipulation to solve for a particular variable depending on which equation we're using. They can never be used over any period of time during which the acceleration is changing. You must have a constant acceleration in order for these kinematic equations to work. There are 4 variables. If the values of 3 of the 4 variables are known, then you can solve for the 4th variable. Okay? Which equation you use depends on what information you need, what variable you're trying to solve for, as well as what variables you already have information for. There is literally no substitute for just doing practice. So the big focus for today is to just keep practicing and practicing and practicing and practicing. And that's what you really have to do, is just get to a point where you're comfortable. Please do a diagram, write it down, establish your directions, write out your knowns. What do you have that you already know? Is it this variable, that variable, or another one? And then go ahead and solve with the appropriate equation. Let's go ahead and do a practice problem so that you can go ahead and see how this works. Young lady named I'm a Hurrian is approaching a stoplight moving with a velocity of 30 meters per second in a positive direction. The light turns yellow and Ima applies the brakes and skids to a stop. If Ima's acceleration is negative 8 meters per second squared, okay, meters per second squared, it's an acceleration, but notice that it's negative because we're braking, so it's opposite the direction of motion. Then determine the displacement. So remember, displacement is distance of the car during the skidding process. All right, so first things first, we need to do our diagram and identify our knowns. In this instance, we know that the acceleration is negative 8 meters per second. In this diagram, you can see the movement of the car, where its initial velocity is 30 meters per second, and its final velocity is 0 meters per second because it comes to a stop. We want to know how far it travels in that time period. So if we write out our givens, we have VI equals plus 30 meters per second, VF is 0 meters per second, A is negative 8 meters per second squared, and we need to solve for D. So what kinematic equation are we going to use? Now, the best one, and I would encourage you guys write these down, okay? So you can go back to the previous slide. These are the 4 kinematic equations that you need to have access to, and you're going to be able to use as you go through your quiz, etc., your test, etc., okay? All right, so back to where we were. The best one for this particular setup is to go ahead and use VF squared equals VI squared plus 2AD, because we have VI, we have VF, we have A, and we're trying to solve, in this case, for D. Okay? All right. So then we simply substitute and solve. When we go ahead and do this, I want you to pause the video here and then go ahead and practice. Okay? When you're done practicing, come back and then we'll go ahead and take a look at your answer and see if we can go ahead and find out how you got there. All right, pause the video here and give this a try. Okay, welcome back. So hopefully you have an answer. Let's go ahead and take a look and see if we can come up with the same answer. So again, remember we have our givens. Oops, I'm writing too thick and dragging my pen. Let's try this again. All right, so we have VF, which we know is 30 meters per second. But this is squared equals VF. Wait, sorry. So let me go ahead and erase that. I wrote the wrong number. See, this is why you have to pay attention to details. So this is 0 meters per second because this is VF equals 30 meters per second. And this one is squared also. Plus 2 times A. We know A, negative 8.0 meters per second squared. And D, which we don't know. That's what we're going to solve for. Well, 0 squared is still 0. So this is going to be 0 meters squared per second squared equals 30 times 30 is going to be 900 meters squared per second squared. Keep track of your units. Plus 2 times 8 is 16. Negative 16 meters per second squared d. All right, so we've got the same units. We're going to move this across. We end up getting negative 900 meters squared per second squared equals negative 16 meters per second squared d. We want to get d by itself, so we divide both sides by negative 16 meters per second squared. Okay. Divided by negative 16 meters per second squared. And then we just simply have to go ahead and do the math because these are going to go ahead and cancel out, leaving us with just d. And this leaves us with, okay, we can try and cancel some units. Meters, 1 meters, second squared. So we're going to be left with a distance in meters, which sounds perfect. So then we end up with d equals, and the answer we go ahead and get here is 56.3 meters. Sorry, I kind of wrote on that a little bit. I thought I had my spacing good. But okay, so that's how you go ahead and solve for it. Make sure you know what your givens are. Do your diagram. Once you've done that, then you pick the correct equation, substitute in your knowns, and solve for the unknown variable, in this case distance, and we got 56.3 meters. Okay? All right. Now, that's a good example, and like I said, there's really no, substitute for just practicing. But some other things I want you to keep in mind. Most real-world kinematics problems involve motion in 2 or even 3 dimensions. And this should come as no surprise since we live in a 3-dimensional world. Fortunately, most of the equations from the previous slide can easily be generalized into 2 or 3-dimensional cases by simply using directions, okay, and then breaking it down into component vectors. The prescription for doing this is really simple. Instead of treating position, velocity, and acceleration as scalar valued functions, we reinterpret them as being vector valued by having a particular direction, x of t being a number or scalar, and the value of the function with that particular direction. Okay, so let's give you an example. We have a ski resort, okay? And we're going to go ahead and look at motion, but this time it's just not back and forth. So at a local ski resort, you take a tow rope to the top of the bunny slopes. I was going to take the kids skiing. We didn't get to it, but we did go sledding. Your displacement vector for this trip has a length of 190 meters. So right away, hopefully you're recognizing that this is a distance, and points at an angle of 26 degrees above the horizontal. So we're not going just horizontally, we're going up and to the right. So during the ride to the top, how far have you gone in a horizontal direction? And how much have you gone in a vertical direction? We can use this to go ahead and find the elevation climbed as you took the tow rope up to the top of the bunny slope. So number one, sketch out a diagram. I would recommend a free body diagram of the motion of the skier that maybe it doesn't have to be this detailed, looks something like this. Okay, so there's theta showing you the angle, which we have from the previous slide, right? 26 degrees. We have the distance of the vector. Okay, the vector for this trip is 190 meters, and that's d vector, okay, the one at the hypotenuse. And what we're going to go ahead and do is we're going to go ahead and try and find dx and dy so we can go ahead and take a look at our needed materials that we have here. Okay. All right, so back here. During the ride to the top, how far have you gone in horizontal and a vertical direction? Now, in order for you to be able to do this, you need to go ahead and think about right triangles, and this requires us to use sine, cosine, and the Pythagorean theorem. Okay? And as we go ahead and do this, we can go ahead and start to solve. Oop, I went backwards. Okay. We have d of x, which is the horizontal, remember. So I'm going to draw this over off to the side so that we can go ahead and see this. Just really small, smaller version of what we just did. I'll exaggerate it so it's easier to see. This is d of x. This is d of y. And this is our d that actually equals the vector quantity, which is equal to 190 meters. Okay, so when we go ahead and do this, we know that this angle is 26 degrees. And so we can use this to go ahead and solve. Now, d of x is here, and we should know that when we start looking at cosine, right, we can use SOHCAHTOA, right? Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. And so this is going to be a good friend to you when we start doing component vectors. So I would highly encourage that you make sure that you know how to do this and that you know how to use it. Okay? So if we go ahead and solve this, this one doesn't require you to use a kinematics, but this is how you break it into parts if you need to separate it out so that you can do a vertical component and a horizontal component. And then we can go ahead and solve. And as we go ahead and do so, you begin to realize that you get d of x is 170, so they do a lot more horizontal, but they do rise 83 meters, which is d sub y. Okay, so please jump in, do some practice. My big hints for you today are write it out. Okay, start by drawing your diagram. After you've drawn your diagram, identify your frame of reference. Then you need to go ahead and identify your variables. What do you know? What are your knowns? And what do you not know? What are you looking for? Then you can go ahead and pick the appropriate kinematic equation to solve for the needed variable based on the variables that you have. All right? That's what I've got for you today, guys. Hope you have a great day. Take the best care of yourself you can, and we'll talk to you soon. All right, take care. Bye-bye.